The transport layer is responsible for providing logical communication between application processes running on different hosts. In contrast, the network layer is tasked with delivering packets from the source host to the destination host, irrespective of the application. The key function here is routing, deciding the path a packet takes through the network, and forwarding, which is the hop-by-hop movement of packets through intermediate routers. The primary protocol operating at this layer is IP. The TCP/IP protocol architecture defines how data is transmitted across the internet in a layered manner. Each layer in the stack is responsible for a specific set of functions and hosts particular protocols. At the application layer, we find protocols such as HTTP, FTP, SMTP, and Telnet, which enable user-level services and direct interaction with software applications. These protocols rely on the transport layer to communicate. The transport layer is represented here by TCP and UDP, which provide logical process-to-process communication. The network layer includes protocols like IP, which handles the routing and addressing of packets between hosts, as well as ICMP and OSPF, which support control and error messaging and dynamic routing. The data link layer includes hardware-level protocols and technologies responsible for node-to-node data transfer. It also hosts address resolution protocols such as ARP and RARP. We can categorize the protocols between three operational planes. The data plane, which is responsible for the actual transfer of user data. The control plane, which uses protocols like OSPF, RIP, BGP, and ARP to support routing decisions and path setup. And the management plane, which involves protocols such as ICMP and SNMP to detect, report, and manage network faults and configurations. In the network layer, the data plane carries user data from the source to the destination. A critical point here is that network layer protocols are implemented both in end hosts and in intermediate routers. While end hosts initiate and receive data, routers serve as forwarding points in the path. Each router examines the IP header of incoming datagrams to determine the appropriate next hop toward the final destination. This decision is based on routing tables that were computed by the control plane. The process of forwarding is hop by hop. Each datagram is forwarded independently from one router to the next, without the routers maintaining end-to-end connection state. The network layer offers several essential services that enable scalable and efficient data communication across interconnected networks. The first core function is addressing. Each host or router must have a unique identifier, specifically a unique IP address assigned to its network interface. This allows data to be directed to a specific destination on the global internet. Next is forwarding, which is a local operation performed by routers. When a packet arrives at a router, the forwarding function determines which output interface the packet should be sent to, based on its destination IP address and the router's forwarding table. Closely related is routing, which is the global process of computing paths across the network. In addition to these core functions, the network layer also supports several auxiliary services. ICMP is used for diagnostics and error reporting, for example in tools like Ping and Traceroute. Protocols like ARP and DHCP support address resolution and dynamic assignment, which are essential for host configuration and communication in modern networks. Routing is a global process driven by the routing algorithm, which runs on each router to compute optimal paths through the network. These paths are based on various metrics, such as hop count, delay, or administrative policies. The result of this computation is a forwarding table or routing table, which is stored locally at each router. Forwarding, on the other hand, is a local operation. When a packet arrives at a router, the router extracts the destination address from the packet's header. It then consults its forwarding table to determine the appropriate outgoing interface or output link for that packet. The diagram in the slides shows this process. The value 0111 from the packet header is matched against entries in the forwarding table. Based on this, the packet is sent to the next hop via the corresponding output link, that is link number 2 in this case. In IP version 4, an IP address is a 32-bit binary number used to uniquely identify a network interface in an IP-based network. While machines operate on binary values, this format is not human-friendly. Therefore, for readability and usability, IP addresses are written in what is called dotted decimal notation, where each segment corresponds to 8 bits or 1 octet of the 32-bit binary address. Each octet can range in value from 0 to 255, which is the decimal equivalent of 8 binary bits. This notation helps both administrators and network protocols quickly interpret and configure network addresses. It is important to understand that while we see decimal numbers, all processing internally is still done using the 32-bit binary representation. It is important to note that each IP address is uniquely associated with a specific network interface, whether on a host or a router. This uniqueness ensures correct identification and delivery of packets across the network. An IP address must also have universal significance, meaning it must be recognized and routable across the entire internet. IP routing relies on the destination IP address embedded in each datagram. Routers use this destination address to determine the appropriate path toward the final recipient. Moreover, IP addresses are not assigned arbitrarily. Instead, they are allocated in contiguous blocks to organizations such as Internet Service Providers, ISPs, or enterprise networks. In IP networking, a network is defined by a block of contiguous IP addresses, and these addresses must share a common bit pattern in the first n bits. This shared portion is known as the network prefix or net ID. The 32-bit IP address is logically divided into two parts. The first n bits represent the net ID, which identifies the network itself. The remaining 32 to n bits form the host ID, which identifies a specific interface, often a host, within that network. For example, in a /24 network, the first 24 bits are fixed as the prefix, and the last 8 bits are available for assigning to hosts within that network. Originally, the 32-bit IP address space was divided into 5 address classes, labeled A through E. Each class is defined by a fixed number of bits for the network ID and host ID, and the initial bits of the address determine the class. Class A addresses are designed for very large networks. The first 7 bits identify the network, with the first bit fixed to 0, and the remaining 24 bits identify hosts. This allows for 128 networks, with over 16 million hosts each. Class B is used for medium-sized networks with a 14-bit network ID and a 16-bit host ID. Class C addresses support many small networks. They use 21 bits for the network and only 8 bits for the host. Class D is reserved for multicast applications. Class E is reserved for future use and experimental purposes. While classful addressing has been replaced by more flexible methods like the classless interdomain routing, we will see it in the next slide, understanding this historical model helps explain how early IP networks were structured and why address exhaustion became a concern. The classless interdomain routing was proposed in the early 1990s and officially adopted in September 1993 through Requests for Comments, or RFCs, 1517 to 1520. Its primary goal was to enable more efficient use of IP address space. Under the classless interdomain routing, an IP address is expressed in the dotted decimal format, /n, which denotes the length of the network prefix, meaning the first n bits of the address are fixed and define the network. The number of available addresses in the block is 2 to the power of 32 to n. For instance, a /19 block provides 2 to the power of 13, that is 8192 IP addresses. The example shown in the slide represents 8,192 contiguous addresses, starting from first address and ending with the last one. You can see how the binary representation helps identify the starting address and confirm the prefix length. The classless interdomain routing allows for flexible and fine-grained allocation of address blocks. The net mask is a 32-bit binary value used in conjunction with an IP address to identify the network portion of that address. It is important in determining which bits of an IP address belong to the net ID and which are reserved for the host ID. The net mask consists of the first n bits set to 1, where n represents the length of the network prefix. The remaining 32 to n bits set to 0, representing the host portion. Net masks can be represented in either dotted decimal notation or prefix notation, for instance /24, which simply indicates the number of ones in the mask. The example provided shows the IP address with its net mask. By applying the net mask to the IP address via a bitwise AND operation, we derive the network IP address. This process allows routers and hosts to identify the network a given address belongs to, and enables routing decisions and subnetting in IP networks. There are alternative ways to represent the same network identifier, NetID. which is useful in routing tables, documentation, and configuration. In the example, the network is associated with a 16-bit prefix. This means that all IP addresses in this block share the first 16 bits. Since 16 bits are fixed, the block includes 2 to the power of 16 possible addresses. This network can be written in multiple equivalent forms, as a pair of address and net mask, or as an explicit address range. An IP network address is composed of a group of network interfaces, whether belonging to hosts or routers, that share the same network prefix. All interfaces with IP addresses within this prefix range are considered to be on the same IP network. Importantly, these interfaces must also be physically interconnected. This typically occurs via switches, hubs, or other layer 2 technologies that enable direct frame transmission. In this diagram, hosts A and B, with their IP addresses, along with router interface C, are all part of the same IP network and can communicate directly at layer 2. However, to reach other IP networks, we require at least one router with an interface connected to this network. This router will forward packets destined for other IP networks. In this case, interface C serves as the default gateway for hosts A and B. The dual homing refers to the scenario in which a host or router is equipped with multiple network interfaces, each connected to a different IP networks. Dual homing is common in both enterprise and multi-homed residential setups. For instance, a server may connect to both an internal network and an external ISP to ensure redundancy or support policy-based routing. However, it is crucial to note that each interface of a device must belong to a different IP network. IP addressing rules prohibit assigning 2 interfaces of the same device to the same subnet, as it leads to ambiguous routing behavior and potential loop conditions. The IETF has defined 3 blocks of IPv4 space for private use, which are reserved for use within private networks and are not routable over the public internet. These addresses are non-unique globally, meaning the same private address range can be used by multiple organizations independently without conflict. Devices within such networks can communicate freely using private IPs, but they require translation mechanisms to communicate with external networks, such as the NAT, that stands for Network Address Translation, which maps private IP addresses to one or more public IP addresses. We'll examine NAT in more detail in a later module.